Now the final quantity we care about in dynamics is momentum. Now this is not an exhaustive list. There are more quantities that we care about, but for now we can stop at momentum. So it is a quantity of motion, a measure of how much oomph a body has in it. It's very difficult to describe momentum, but you can relate it to force. So the force is the rate of change of momentum. So if we want to increase the momentum significantly at very fast, we're gonna have to have a high force. If we're gonna if it's something that we want to change the momentum of very slightly, right, and over a very long period of time, we only need a very small force. So momentum, sometimes you'll see rho, sometimes you'll see P as being P equals mv. But the formula for momentum is equal to mass times velocity. Mass measured in kilograms, velocity measured in meters per second. So unit for momentum is kilogram meters per second. Right? So momentum is like energy in that momentum cannot be created or destroyed. This is called the conservation of momentum. So it turns out not only is energy conserved, but momentum is also conserved. And that's very useful for us, especially when we're looking at like objects colliding and we're looking at how much velocity is there finally, how much velocity was there initially, that sort of thing. That's very useful for us. Yep, so collisions. In physics, a collision is defined as an interaction where two or more bodies apply forces to each other in a relatively short period of time. So there are two types of collisions. There are elastic collisions, a collision where all kinetic energy is conserved. So that's, for example, a rubber ball, a very bouncy rubber ball on a hard surface, for example. That is an elastic collision, or like very close to being an elastic collision. In reality, no collision is perfectly elastic because you have kinetic energy lost to other forms, but like heat or sound or sometimes light. But a rubber ball on a hard surface is very close to an elastic collision. But if you think about inelastic collisions, right, that's a collision where some kinetic energy is converted to other forms. And extremely inelastic collisions or very inelastic collisions would be something like a ball of Play-Doh, for example, which is very moldable, and it gets thrown on the ground. It sort of doesn't bounce very high. It might just sort of flatten itself out a bit, right, and it doesn't bounce. So that in that case, you've got a high kinetic energy initially when you're throwing it, but then at the end you've got like pretty much no kinetic energy. In that case, it's an inelastic collision. Now, in general, all collisions are inelastic because you lose a lot of energy in a variety of forms. Even if you lose a small amount of energy, it's still considered inelastic, but you can approximate a lot of collisions as elastic if you assume that you don't lose a lot of energy. Momentum is conserved in both cases, so whether it's elastic or inelastic, both cases, momentum is conserved. Now, why is momentum useful? Well, because we can look at collisions like these ones. So you've got a 1,000 kilogram car, and it's stationary, but it's struck by a 1,800 kilogram van traveling at 50 kilometers per hour. The two vehicles lock together in a collision, which you can assume is elastic. What is the speed of the vehicles immediately after the collision? So if we have the ground, and you've got a 1,000 kilogram car, for example, maybe I'll move over. So you've got a 1,000 kilogram car, 1,000 kilogram, and then you got a bigger 1,800 kilogram van. And it's moving at 50 kilometers per hour. Now, in this case, I'm not going to convert units because, and you see why, but in general, you do want to convert to SI units, so you want to turn kilometers per hour into meters per second by dividing by 3.6, I believe. But in this case, it's safe not to. But if you're ever in doubt, convert units and then reconvert back. But if you're sure that the units are going to cancel out, like it's going to happen here, that's perfectly fine. You can leave it in kilometers per hour. So let's just say we've got this 1,800 kilogram van that collides with this 1,000 kilogram car. The van's initially going at 50 kilometers per hour. After they collide, they actually lock together. They're sort of joined together, and then they move together, right? And you see that in a lot of questions because it avoids the need for simultaneous equations and avoids the need for assuming it's a perfectly elastic collision. But in this case, we don't need to assume that because we're going to use just the law of conservation of momentum. So the net momentum initially is equal to the net momentum finally. So let's look at what the net momentum is initially. Initially, we've got only this object moving, right? Not this object. This object initially has zero velocity, so it has no momentum. So initially the momentum is all towards the right, and momentum is actually a vector quantity because it's mass times velocity. Velocity is a vector, mass is a scalar, so it's just so all it does is take that velocity vector and scale it by a factor of the mass. So net momentum initially is 1,800. So actually I'll write the formula. Mass of the van times the velocity initial of the van. So you get mass of the van, which is 1,800, times the velocity initial of the van, which is 50 kilometers per hour. And I'm going to use kilometers per hour here because we can. In this case, we don't have to actually convert units. It's going to keep the numbers a bit nicer. But if you're ever in doubt, actually do convert. I'll show you why we don't have to convert in a second. So you have 1,800 times 50 is 90,000. Sorry. 90 times 10 cubed kilometers per hour. Sorry, kilogram kilometers per hour. Yep. So that's the initial momentum. Next, to sort of make use of this equation, we want to look at what the net momentum is finally. What's the net momentum finally? Well, that's going to be dependent on the total mass after they lock together. So you've got 1,000 kilograms plus 1,800 kilograms. So the mass total times the velocity final of the sort of conglomerate mass. So you've got 2,800, which is the total mass, times the final velocity. And here's why I can use kilometers per hour. Because we're going to have the masses cancel, right? The kilograms part is going to cancel, and we're going to get our final answer in kilometers per hour. So in this case, it is okay to use kilometers per hour. But again, like I said, if you're in doubt, convert to SI units. So we can say 90 times 10 cubed is equal to 2,800, which is the conglomerate mass, times the final final velocity of that joined together clump of cars, of van and a car. So in that case, we have VF is equal to 90 times 10 cubed, 10 cubed divided by 2,800. So we get 90 times 10 cubed divided by 2,800. So we get approximately 32.14 kilometers per hour. And again, this is why we can use kilometers per hour, because the kilograms cancels out. So this would be kilograms kilometers per hour, and this is this is just kilograms. Kilograms cancel out, so we're left with 32.14 kilometers per hour. So VF equals 32.14 kilometers per hour. Kilometers per hour. Here we only relied on conservation momentum, but if we did want to rely on conservation of kinetic energy, we can. We could have used kinetic energy initial equals kinetic energy final, because it does say that the collision is elastic. So is momentum just a totally separate thing? Well, no, because applying a force changes velocity and thus changes momentum. This is called impulse. So impulse is linked to the force applied and how long it is applied for, and it's quite easily proven. So for example, we've got change in momentum. So the rate at which, or the change in momentum is equal to force times time. So this force times time is called impulse. Sometimes you see I being used, capital I or J even, being used for impulse. So impulse equals force times time, right? And that's equal to the change in momentum. So if we have a force and it's applied over a distance for some, so let's say we have a rock and then it's got a force applied onto it for some period of time, it changes the momentum because it's accelerating, right? And the velocity changes. Even if the mass is constant, velocity changes. So that means that there has to be a force applied because there's an acceleration. So impulse results in a change in momentum. And this formula explains many things. So for example, crumple zones. So if we look at F equals to, if we rearrange for change in momentum over time, right? You can say mass times velocity final minus mass times velocity initial, assuming the masses are constant. We can actually pull out the factor of mass, and we can say VF minus VI over delta T. Now that's just acceleration, so it's mass times acceleration pretty much exactly. But what we see here is that the force is dependent on the change in momentum over time. So the rate of change in momentum. So if we can slow down how fast that change in momentum occurs, it results in a lower force. So that's why crumple zones exist. If you can change that momentum over a longer period of time, right, that results in a lower force produced, right? Or if you it occurs over a longer distance, taking a longer time, therefore it decreases the force that's experienced by the passengers. That's why crumple zones are effective.